welcome all my teaching and non-teaching colleagues and also students for this session. The topic of discussion for this session is cyber security issues in Internet of Things. So I now call upon Dr. Anish Arora to take over the session. Over to you, sir.
Thank you. Very happy to be here and get a chance to talk to you. Now, can everybody hear me? Yes? Am I clear? Is it what I'm saying makes sense? Okay, that's great. And can you see everything on that screen? Okay, great. So, this is sort of an exciting, complicated topic. And it's sort of happening as we speak. So it's an area where the world is changing and you can have a chance at influencing this area because things are so basic right now. So what I'd like to do is to walk you through the elements of cybersecurity in the Internet of Things. Yeah? Now don't hesitate to stop me at any point. This is not intended to be a deep research talk. Yeah? It's about very simple principles, very simple problems, very simple approaches, because that's where the state of our art is right now. Okay? So stop me if anything is unclear, and don't feel embarrassed if you think your question is too simple, or maybe even the wrong question. There's no such thing as a wrong question. Just stop me and ask, okay? Is that a good enough contract? Yes. Okay, very good. So I want to begin with something that a Turing Award winner said. His name is Graham Bell. And what he said was the nature of computer science is that every 10 years we come up with a new generation of computing. There's a new platform that we use, Well before you were born, we lived with these massive machines, which at some point became called mainframes. And for that type of computing, we needed a specific type of hardware, a specific type of software for programming it, a specific type of network for input-output, and interfaces by which you could interact with that device. And that gave a certain type of application and created its own industry. And every 10 years, that industry keeps changing. Right? So if you look at where we are today, the mainframes were replaced at some point by machines which were trying to do symbolic computation, by machines which, were much smaller, but still could do heavy enterprise-level computation. And then the personal computer came. At some point, the personal computer was connected to the web, and computing started shifting to the web. But that was a very simple use of some computing that was far away from us. And then came the generation, where from cloud computing, much more computing came back into your pocket. So no longer PCs and laptops. The smartphone has been the generation of computing that you have grown up with. But now, the next generation of computing that is here is possibly IoT. Yeah? So the Internet of Things is going to create a very large number of devices which will be, in some sense, connected. Yeah? So today, the number of smartphones that is selling is much higher than the number of laptops and PCs that are selling. Yeah? Today, the number of chips that Apple sells is much higher than the number of chips that are sold for servers and other cloud computers. Yeah? So the technology that we are dominated by has changed. Yeah? But now this new technology is going to take over. So how many smartphones can I have? Maybe I need just one. When I'm traveling in India, perhaps I need two. I have another phone here. Yeah? But we are only a few billion people. So we'll have only a few billion smartphones, right? But today, the number of IoT devices is far more than the number of billion phones that we can have across the world. And this number will keep growing exponentially. So in the next decade, computing will increasingly involve our dependence on IoT technology. Now, in this column, I was sort of giving an example of what was the main representative, hardware or software system that characterize each generation of computing. And now we can ask the question, well, what is the software or hardware that is dominating the IoT ecosystem? Is there one? Doesn't seem to be clear if there is going to be one. There certainly is not one today. So I'd like to explain that point in the next few slides. When the PC was introduced, the main application that sold the PC was word processing. Yes, I can have a computer to write, not on a piece of paper. I can write a paper on a computer. Yeah? Now, you have to go back to 1980 to understand that the significance of this. At that point, these mini computers were very powerful. They could do very interesting giant simulations. Yeah? So if somebody gave you a small computer and you said, go home, and what you can do with it is you can type a document, people would think it's a toy. Yeah? Why would you take a toy when you've got a powerful computer that you can use, right? And my first computer I got when I was probably 1979 or 1980. It was an 8-bit machine. Yeah, it had a touch keypad. I had to connect it to the TV. And all I could do was write a basic program so I could move a ball from one wall to another wall. Yeah? So it was a toy. Yes? And that's the nature of computing. Every generation introduces what appears to be a toy, but soon this toy becomes so powerful that it displaces our mental model of computing. Yeah? So 15 years ago, our mental model of computing was here. And when the smartphone came, a lot of computation started happening inside our pockets. Yeah? We can do deep learning engines inside our pockets. Yeah? So today when you see IoT, I'll show you examples which look like toys. But interestingly enough, they are quite capable, and their capability will grow extremely fast until they start dominating your mental model. Right now, everybody who wants to go into computer science wants to learn how to write apps. Yes? Your mental model is dominated by, this will give me a good job, apps are cool, I can write a killer app and make a lot of money. Okay? But tomorrow your mental model will shift about how to program these IoT devices. So be prepared for that shift. Okay? That's the nature of computing. So going back to this question, what is the key software, the key hardware, the key application of IoT? The point I'd like to make is, in fact, we don't know. The word thing is just a very loose term. It has many, many meanings, and it has many, many forms. So let's take a slightly deeper dive into what a thing is. So let's look at applications from the consumer space. A thing could be something that just sends out a beacon. Yeah? There could be a beacon in this room which says, you are in room ground floor seminar hall. Yeah? That beacon is picked up by your phone, and your phone sends a message to the cloud saying, I, Anish, picked up the beacon in the ground seminar hall. And now the cloud knows that I am attending this class. So we can take your attendance using beacons. Yeah? It's a toy, it's a very small toy, but I no longer have to ask you, are you present? Right? I automatically know whether you're present or not. And when I'm giving you an online test, and I can check that you're not here, I know you may be at home and cheating in the online test. Okay? So things are becoming simpler in that sense. Now, this is a slightly more interesting sensor. It tells you how to control your room. You can do it wirelessly. From here, I can go to my house in Ohio, and I can see what the temperature is, and if it's too high, and I don't want to waste energy, I can lower it from here. Very simple. If I just want to order a new, soap, I can press a button, and that button knows if I press this button, fill up the soap by sending a message to Amazon to deliver that soap. Yeah? A smart lock can figure out whether you are close to it and open automatically. It can take a look at your face and do face recognition. Yeah? It can send that image or a video stream to a phone app. So all that can be put into something this size and run on batteries for a few months. And of course, some of you are probably wearing Fitbits. You can do all kinds of activity tracking. So these are just consumer space applications. Yeah? And how do you build them? What are the underlying pieces of hardware? This could be a simple 8-bit microcontroller. How many of you have heard of Arduinos? That's wonderful. Yeah? So all of you know that you can make your own IoT device by getting a very simple programming platform where you're programming essentially on bare metal. You don't need a fancy operating system. I can just write C and program it on the Arduino. Or you can have a slightly more capable microcontroller. This is the device that we make in my company. And there are many such devices out there. It has a 32-bit processor. It has a radio on it. It has significant amounts of storage on it. I can have a small display here which you can delete. You can connect any number of sensors. And so with this, you can have a very small operating system, an operating system that probably we had back in the 1990s. But today, that 1990s operating system is so powerful that I can run virtual machines on it. I can run virtual networks on it. Yeah? Still very small. Yeah? Not as big as what your phone needs. Of course, if you want to be more powerful, many of you are familiar with the Raspberry Pi. Here, you've gone from a battery-powered device to a device that is wall-powered. But now you can do video analytics on this. So you can do video streaming, HDMI, all of that, many more interfaces here. Or in fact, you can have an even more capable device which has got some reconfigurable logic in it. And now, instead of thinking about your radios as a piece of hardware or as a dedicated chip, you can think about your radios as simply the acquisition of a signal, an analog signal. And everything that the radio was doing in hardware, you can do in software. So you can have a software-defined radio. Yeah? And that too is a thing. So things have many different physical forms. And of course, many other applications. You can have drones. You can have, this is a very common use case of industrial IoT. Yeah? All industry is trying to monitor the state of its plant, how things are working, what is not being used, and automatically they can take decisions on if there's a maintenance problem or a lack of use problem or an underproduction or overproduction, state estimation. That sort of thing can be done by collecting data over IIoT. And the cars that you are using, probably your car is certainly telling you, right, that there's something behind you when you're backing up. Sometimes it'll tell you on your side view mirror that there is a car beside you. But Mobileye can actually do discrimination of, there is a bike in front of you. There is a bike coming from the right side of you, right? Or there is a car that can give you all those alarms. So all that is done on a single device inside your side view mirror, and it's coupled to your display. So you can be a safer driver. Yep. Again, this list of IoT applications is so large that it's an almost pointless exercise. I'm just trying to motivate the point that IoT has too many forms and not a single concept that is dominating it. So let's take a look at those three examples a little bit more deeply. The Arduino or the moat is running at a relatively low speed. It's consuming a relatively low amount of power. So I can run it on batteries. Yeah? The Raspberry Pi is actually not just one microcontroller. In fact, it's more like a proper application processor. So this is the application processor in the Raspberry Pi. And in fact, it's got a graphics engine in it. Yeah? So you can do not just rendering, you can do sophisticated math data analytics on that device. But now the price you pay is that your power has gone up by a factor of 10. So you remember the 0-watt bulbs that we leave inside our houses at night so that kids feel safe? Actually, their power consumption is on this order. It's about a 1-watt, 2-watt power consumption. Okay? And that you don't use batteries for that necessarily. So this is a non-battery powered device. But now if you look at your smartphone, now a smartphone can have many, many different types of processors. It can have microcontrollers, microprocessors, application cores, GPUs, FPGAs. Your microphone in your pocket probably has about 12 processors. So just imagine the amount of computing that you have inside your purse or your pocket. Yeah? It's like a mini data center inside your pocket. There is that much ability to program on that smartphone. But the other point that this slide makes is that we are no longer programming on one computer. We are increasingly programming on multiple computers. So heterogeneous computing is the norm, and even for modes, we're finding that we can run at this power with multiple processors. So yesterday I was explaining an application that I'm building for New York City where I'm looking at sound complaints. I'm trying to figure out, is this a car honking? Is this a baby crying? Is this a construction sound? Different types of sound issues. And to do that, we are doing it on battery with a moat which has got literally all of these types of processors, but much smaller. And you can run all of that on a battery for many, many months. Now, these devices coming to cybersecurity are now starting to include some security support inside them. Yeah? So in addition to all these processors, I can have a little bit of silicon, which is doing dedicated computing for security operations. Yeah? Sometimes if I want that to be not pure hardware, like an application-specific integrated chip, I can have something that's programmable. I can have an FPGA inside my IoT device, and that FPGA has got some security features in it. So at the mode scale, you remember I had just a single microcontroller? Now I add an FPGA to it, and that FPGA can do encryption using a symmetric key. It can do hashing. It can do random number generation. And by the way, when you get to the bigger FPGAs, you can start putting in more interesting security programs, which you normally include in the kernel of a system. So how many of you are familiar with the word kernel in an operating system? Just a handful, right? So how many of you are familiar with operating systems? Okay, many more people know that most of our machines actually have an executive called the operating system. The core of that executive is a kernel. The kernel often includes some very protected operations, and the idea that you can boot a machine in a secure way is one such protected operation. But I can take that function out of the kernel and put it inside the FPGA. So now that makes it even more secure from a use point of view. That if an application compromises the operating system, it may not be able to compromise the secure boot. So it may not be able to overtake the whole machine. If we realize that the operating system is corrupted, we can reboot safely from the FPGA the whole machine. And by the way, you can have an even bigger FPGA. So you can almost put at this scale, you can have devices which can give you the power of writing like a base station controller. You know you have those tall towers where all your cell phone signals go to. Basically, in those towers, there is a small machine called a base station. And those computers in the base station can now be replaced with small devices of this scale. So now, even that infrastructure is going to become more programmable using this type of IoT. So what was the point here? Many different types of hardware, and some of them have support for security. Now let's go to the software side. Is there a popular software and popular operating system? Well, on the Arduino, we saw we can program on bare metal. Maybe you can put a small real-time operating system like FreeRTOS. Or you could have another type of operating system. For example, we use a version of the .NET micro framework, which lets you put a small virtual machine. And in your virtual machine, you can program in C#. Okay, another thought question. How many of you know C? Great. So many of you are familiar with C, and several of you are probably programming in C. How many of you know Java? Okay, slightly fewer. And so C# is just like Java. Right? It's Microsoft's language, which is object-oriented at a high level and works on virtual machines. So with an operating system like the eMote, you can program in C#. But it's far less powerful than running Linux or Android, which you are used to on your phone. So different IoT devices will have very different operating systems. Yeah? Similarly, they will have very different types of radios. Your phone has got Bluetooth in it, your phone has got Wi-Fi in it, but some of these IoT devices will use really short-range, low-power communications. So there's sometimes these are called Zigbee radios for 802.15.4 communications. So, you know, I can go 30 meters, maybe 100 meters. But if I want to go many kilometers, I can use a different type of radio, which is called the long-range radio. LoRa is the standard, which lets you go at certain low frequencies across long distances. But here, you can transmit at many megabits per second, yeah? Whereas here you can transmit at a much lower rate, maybe just a single megabit, a few kilobits, yeah? Or even a few bits if you want, because IoT often doesn't need very high amount of data. Similarly, the networking has changed. Now, how many of you have heard about TCP/IP? Good. So about a third of you have heard about, you know, the Internet Protocol. That in the past, all of our devices had an Internet Protocol name, like an IPv4 or IPv6, and we tried to use as much as possible either streaming communication or reliable communication on top of the IP protocol. And then we built other protocols, application-level protocols above TCP/IP. But in the IoT space, we cannot necessarily assume that every device will run TCP/IP. Some of these devices are so small, or there are so many, yeah? Or they're all sharing the same channel, the same limited amount of bandwidth, that we can't use TCP/IP as an adequate basis for doing reliable comms with them. Similarly, what happened when you came up with lots of IoT devices whose hardware was different, whose software was different, and whose network was different, what the industry did was that it started preparing itself on the cloud to receive all this IoT data. But the nature of industry is to have a lot of competition, so we have many, many industrial providers of consuming IoT data. So Amazon has its own IoT system. Yeah. Most recently, they released something called, I think, Amazon Lambda. Which one were you thinking of? Oh, Alexa is an application, right? Let's think about the cloud infrastructure that receives, you know, data from many IoT devices. It can control those IoT devices, and then it can let you connect these IoT devices to analytics, and it can connect that analytics to many applications. Okay? So your cell phone application can now receive something from an IoT cloud server. So Amazon came up with something, Microsoft came up with something, IBM came up with something, other smaller companies, yeah, came up with their own cloud infrastructures, and nobody has won. We don't know who will win, or even if one will win. There might be 2 or 3 or 4 cloud infrastructures where all the IoT of the world will go to in the cloud. And somewhere in between what runs on the IoT device and what runs in the cloud is this area in between, which is growing a lot. So edge computing says that perhaps all the computing is not happening in the IoT device, but if it goes up to an access point, just like your Wi-Fi access point, then I can locate computing at the access point here. I can do computing inside Sahyadri rather than, you know, pay for expensive bandwidth to go into the cloud. So computing is now being distributed across these 3 locations. So all this is sort of bad news. Yeah? Too many choices. Yeah? Should I even learn all of them? The answer is no. Yeah? Even if you learn some of them and you become very good at them, you can be very productive in the IoT space. Yeah? You'll definitely not focus on learning all of them. But how do we simplify building systems with all of these different software, network, and cloud and edge systems? So the idea has been, well, at least let's agree on a communication format. So my edge device will talk to the edge server, will talk to the cloud server over the same format. So perhaps that will be the standardization. And here are examples of protocols being used to standardize communications. This is the constrained application protocol. There is something called the message queue teletype protocol. And these, again, not one has dominated, but at least the number is shrinking. Yeah? So hopefully, this will provide some simplification, even if not much. Okay, so that was the first part of the story. What is IoT? Is IoT even one thing? But it's not. So now let's go to cybersecurity. So this is the part where the world is really changing. So I'm going to give you stories from several domains, right? The first one comes from your phone. Back in 2005, your phone could get corrupted, just like your PC could get corrupted if you downloaded the wrong software on it. Yeah, I left my phone with somebody to fix the battery, and they put in a virus into it because they could touch it, right? They could physically reprogram it to include some device. So this is 2005, 10 years ago. People were spying on what calls you made. They would send your location to a hidden server somewhere. They could read your messages. But today what has happened is that we are having wireless jailbreaks of your smartphone. This happened for the first time, to my knowledge, last year. There was an Israeli cyber arms dealer, yeah, who created a system called Stealth Falcon. And they attacked a particular Islamic activist, I think Saudi Arabia or somewhere. And so they compromised his phone wirelessly. They sent him a text, and just with that text, apparently his phone got jailbroken. But the details of this particular Stealth Falcon compromise are extremely sophisticated. They had to use not one but 3 zero-day attacks in order to construct this piece of software. Does anyone know what a zero-day attack is? Anyone want to take a guess what it means? Loudly. Someone I thought was offering an answer. Okay, a zero-day, people come up with attacks on all kinds of computer systems, right? But if that attack is exploited before it is known, it's called a zero-day attack. So some security flaw was found in some software, and before that flaw became public, and before anyone knew how to patch that flaw, somebody exploited that flaw and wrote a virus or a worm or an attack, yeah, even before it was public. So it's very expensive to construct zero-day attacks. And they used 3 zero-day attacks in order to compromise this code. And what's worse is that this code is actually beautifully written. It's a very elegant piece of code. So whoever was doing this was a very good computer scientist. They must have had very good teachers and thought about computing very carefully. Yeah? So this is not just a criminal, but it's an extremely sophisticated criminal who's doing this kind of attack. Now here's a different example. In 2005, I went to a place called the Idaho National Labs. Idaho National Labs talks about critical facilities in the country. Yeah? So like, what happens in power generation plants, what happens in nuclear generation plants, right? And so you have a lot of SCADA systems, control systems where devices are connected. Motors, sensors, computers are all connected by a network, and you can collect their information. And what they showed in 2005 was that if you could break into one of these networks, and you could compromise a software controller, you could take over a motor, and you could run this motor at really high speed, and the whole generator would blow up. And you could see the fumes coming up in Idaho National Labs. So this was a very, very, provocative demonstration. But it was done by people who were just trying to show that their systems were vulnerable. So let's fast forward. If you go to 2009 and 10, do you remember that the Iranian nuclear uranium refining plants were compromised? There's a very famous virus called the Stuxnet virus, if you can read this word, Stuxnet. So it's believed that the Americans and the Israelis put their heads together to construct this virus. And what happened is very simple. People were told to upgrade the USB driver on their computer. So some operator in an Iranian nuclear plant, he receives a message saying, your USB driver is no longer working, update it. So he updates his USB driver. That USB driver has got a virus which goes into his programming logic controller. So there's a little embedded board in there which the USB driver corrupts. And from there, they start spinning the refining generators for uranium at a speed where all the uranium generators were compromised. So with one virus, you were able to take down an entire nation's capability to refine uranium. Yeah? Very powerful attack. But now the problem is sort of going to a level which is even more. Last year in Ukraine, some power generation plant was compromised, and about 80,000 people in Ukraine had a blackout. So now this one was also a nation-state attack, and it seems like, without being absolutely positive about these things, it seems like the Russians were trying to tell the Ukrainians, if you don't align with the policy that we want, we can stop you from doing business. So now this attack has gone from controlling one activist to starting to control a nation. Okay? Okay, now let's talk about a different type of story. Let's talk about smart transportation. So this story here is about a drone, a UAV. Yeah? So there was an American drone which landed in Iran, and it landed at a location where it was not supposed to land. So we couldn't quite figure out what happened. Yeah? And much later it was found out that the GPS that the drone was receiving, so the drone is navigating by GPS, right? So my job is to go tonight from Bangalore to Abu Dhabi, right? So the GPS will tell me I'm in Bangalore and this is the direction towards, I'm going in the right direction. Yeah? So what the Iranians did was that they spoofed GPS. They kept telling me, I think I'm going towards Abu Dhabi, but in fact they were directing me towards Delhi. So I eventually landed, thinking I'm landing in Abu Dhabi, but actually I had landed in Delhi. And so the Iranians brought down this American UAV into their space by spoofing that signal. And we all depend upon GPS. If GPS doesn't work, I will not catch my Ola or my Uber cab. Yeah? So just imagine if I can compromise Ola and Uber and I can send all the cars to the wrong places, what's going to happen? Okay. But we are entering into a world, where vehicles are going to become autonomous. So this problem is going to grow a lot. So there have been a number of attacks where people compromise cars. They can corrupt the Bluetooth driver inside your stereo entertainment system. From the Bluetooth driver, they can compromise your control network. If they can compromise your control network, maybe your car can run faster than it needs to. Maybe your car can go off-road. Maybe I'm sitting in San Diego and your car is in Seattle and I can start up your car. Yes? And all of those have been demonstrated. So this was a demonstration where two researchers took this Jeep UAV and they did all kinds of games with it. They took over the car, they sped it up, they slowed it down, they drove it off the road, just to prove that if we don't have security for these devices, these IoT things, we can be in a world where we are sort of running into each other. Yeah? Okay, let's look at more examples. So we are entering into a world where we want to make our cities and our rural areas safe, right? But in 2005, some of my colleagues showed that even a small RFID tag can be injected with a little virus on it. So if I have a tag around my cat, right, which is a way in which people can find out, they can probe it and ask, they get that information, whose cat is this, what is the address of this cat. Now, instead of getting the address of the cat, I can get a virus from the cat onto my device. Yeah? So just on a small RFID thing, not even a microcontroller, not even an 8-bit programmer, just a simple storage of a small program which can be computed on a state machine. In that I can program a virus and these small tags can give me viruses. So that's an example of something that we are doing in smart infrastructure. And